Okay, this is an introduction to differential equations, and this is the approximation method of Euler. So this is pronounced Euler. Okay, German mathematician. Okay, so let's talk about Euler's method. This is a numerical method for constructing solutions. So it can also be called a tangent line method, and you'll see why. So here we are going to be constructing approximate solutions to a first order IVP. So here's our IVP. We have our differential equation, and we have our initial condition. Okay, and so basically how this works is we're given an initial point, an initial condition, and we use the slope passing through that point to reach this next point. And then we reset and use the slope at that point to draw that next line segment. And again, we have the slope of the tangent line there, and we use that to reach this next point, and so forth. So this distance here is h. Now keep in mind that's this same h value. H is going to be positive, and this is called the step size. Okay, so this is the step size h. So you could actually say here that x1 is equal to x naught plus h. And you could say x sub 2 is equal to x1 plus h, and so forth. Okay, so our step size is h. And basically this is the formula. This is Euler's method right here. And so what does this tell us? Our y value for n plus 1 is equal to the previous y value, y sub n, plus that step size multiplied by the function, and that's going to be the derivative. You can see that's y prime evaluated at x sub n, y sub n. So this is y prime at the previous point. Y prime at previous point. Okay? And that's what we do. Let's just jump right in. I did want to mention one thing. Note, as h decreases, the approximate solution approaches the actual solution. So basically, with a smaller step size, we get more accuracy. Okay? Okay, let's jump right into our example. Of course, you can use a calculator, or there's computer programs, but we're going to do this one by hand. Use Euler's method with step size h equal to 0.1 to approximate the solution to this initial value problem. Here's our IVP, here's our DE, here's our initial condition, and we want to approximate the solution, and we're going to approximate it at 1.5. Of course, we'll approximate each one of these y values. I always like to make a table. So I like to make a table of n, which is the number of steps. And then I like to have x sub n and y sub n. And then I like to have that little table with columns here. And I will show you that we will begin at step 0 with our initial condition. X value is 1, Y value is 4. That's this initial condition right here, okay? So then if we are going to look at these X values, what do you note? We note that H is going to be equal to 0.1. And of course that was given to us, but we could have determined that. So we can actually now write our first step will be at 1.1, our second step, and so forth. Okay, and this is what we're looking for here. This is y of 1.5. This is our approximate solution at x equal to 1.5. Okay, so what do you notice here? If you can see here that you can make a table that has all of this before you begin. Okay, so I think that's really, really important. So our goal is to find this value, this value, this value, this value, and this value. Okay, so where are we beginning? This is our n. So this here would be y sub 1. This will be y sub 2, and so forth. You can see because of n. So let's go ahead and begin. Y sub 1 is the previous y value plus h, which is 0.1, multiplied by y prime evaluated at the previous point. So there's that. And actually I could have filled in this initial y value of 4. Okay, so what is, and we're going to go ahead and figure that out right here, but let's find y prime evaluated at 1, 4. So we're going to be using this y prime, and that's equal to 1 times the square root of 4, which is equal to 2. So we have 4 plus 0.1 times 2, and we go ahead and get 4.2. So that is our first value here. Let me even make that a new color, 4.2. And I will make this that same color. Okay, now let's do the same thing. What are we looking for here? This is going to be y sub 2, right? So, whoops. Try that one more time. Okay, and so now we're going to have y sub 2, and now y sub 2, remember, we're going to, I'll write this here, y sub n plus 1, the next y value is the previous value, plus our step size, and that's multiplied by the derivative evaluated at the previous point. Okay, so we have y sub 2 is the previous y value. Whoops, I wanted to put 4.2 here. So that's going to be 4.2. Our step size is still 0.1. And now we're going to have y prime evaluated at 1.1, 4.2. Okay, and that's equal to, and let's go ahead and evaluate y prime evaluated. I'm going to do that and do that at 1.1, 4.2, and that's equal to 1.1 times the square root of 4.2, and I'll give you that approximation. Actually, what we want to do is not approximate that, and we want to go ahead and put that in here and then multiply that together. So this would be 1.1 times the square root of 4.2, and we are going to come up with approximately 4.425 5, 4, 3. And you can check that on your calculator. So we have 4.42543. Now, we could go ahead and go on with this, but you will be able to finish that, and I will fill in this table for you. So you could pause the video and check these. So this is 4.67787, and then we have 4.95904, and this y of 1.5 is 5.27081. Using the same method. Why don't I put and so forth? Okay, so what we want to do is therefore y of 1.5 is approximately equal to 5.27081. That was our reason for doing all of this. Let's go back and look at the question. Approximate the solution to the IVP at 1.5. And of course, we evaluated it all of the others as well. But that's when x is 1.5. That is what y is equal to. Now, what's interesting is that we don't even know what y is. So we were able to do this. We found this approximate y value without knowing y. Without knowing y. So it's pretty interesting. Okay, let's look at this next example. Use Euler's method to find approximations to the solution of this IVP. Here's our IVP, there's our DE, there's our initial condition at x equal to 1. And here we're going to be taking a different number of steps. So this would take a lot of computer work, but we'll go ahead and just go ahead and start with a step size of 1. So that will just be one calculation. I do want to point out that the solution of this DE is phi of x is equal to e to the x. Okay, so our solutions will be generating approximations to e, since x is equal to 1. We'll be approximating e. Okay, since we would be e to the 1. Okay, so let's take a look at this. So to obtain approximations, what we will do, make a little table over here. So we could call these n. So n is equal to 1, 2, 4, 8, and 16. So this will be the number of steps. Okay, and so if we have a table of the number of steps, and then we have our step size, and then we could go ahead and find that approximate solution for e. Okay, so if we're given n equal to 1, 2, 4, 8, and 16, you can see that we're going to be taking that 1 over 1. So h is equal to 1 over n. Okay. Okay, so this will be 1, and then here we will have 1/2, so that will be 0.5, and we will have 1/4, so that'll be 0.25. We'll have 1/8, which is 0.125, and then 0.625. Probably didn't do a very good job of that last line. Okay, and now we're going to see our approximations for E using this. Okay, so let's just look at a couple of these. So for n equal to 1, we will have phi of 1, and we're going to be just looking for that y of 1. So y of 1, and this is going to be approximately equal to y of 1, and that's going to be equal to our original y value, which is 1. This was 0, 1, that's our initial condition, and that would be plus our step size multiplied by y prime evaluated there, which would just be 1. So this is equal to 2. Okay, so we've approximated E, Euler's number, to be 2 with just 1 step size. Okay, let's go for n equal to 2. So we're going to take 2 steps here. So the first thing we're going to have is y sub 1. So here, let's keep in mind that phi of 1 is going to be approximately equal to y2. So we need to first find y1. So y1 is going to be equal to our initial y value, which is 1, plus our step size, which is 1/2, 0.5, multiplied by the derivative evaluated there, and that derivative is going to be equal to 1. So that's equal to 1.5. Now we need to take one more step. That's our previous y value plus our step size, and now we need to have the derivative, which is exactly equal to the y value, and that's going to be equal to 2.25. So taking 2 steps, we're getting a little bit closer. For n equal to 3, keep in mind that that solution evaluated at 1 is going to be equal, whoops, we're at 4. Is going to be approximately equal to y sub 4. So we're going to need y1, 2, 3, and 4. Okay, so here we have the previous, and that would be y sub 0, plus here our step size is 0.25, and then that will be multiplied by the derivative evaluated at that point, and that's just at our y value, which is 1. And here we would get 1.25. So going to the second step, we have 1.25 plus our step size multiplied by 1.25, and you'll get 1.5625. Let's go to y3. Here we have our 1.5625. That's that previous y value multiplied by our step size of 1/4. And then the derivative evaluated is just equal to y. So y prime is the y value, that y. 2.5, and that's going to be equal to 1.95313. And finally, that fourth step plus 0.25 multiplied by that y value, and you'll get approximately 2.44141. And you can check these. So that would be 2.44141. Now this would be and so forth for n equal to 8 and n equal to 16. But I will give you those values. If you take 8 steps with a step size of 0.125, you will have an approximation of y of 1, or the solution at 1, 2.56578, and with 16 steps, 2.63793. So as you can see, we are approximating E using different step sizes, or you could say increasing the number of steps. We'll just make one final note here. Note as n increases, the approximate solution gets closer to the actual solution. And that is the same as h getting smaller. And that concludes this lesson.